In the last few chapters, you've probably noticed that we've placed a lot of emphasis on types of reactions and how to go from reactants to products and just kind of looking at the nuances between reagents, reactants, and products. In this chapter, we're going to kind of tie that all together. Right? How do we combine everything that we've learned to get syntheses to work for us? In other words, if we are given sets of reactants and reagents, how can we figure out the different possible products we've got? What's our major product going to be? Or if we have a reactant and a product we're trying to get to, what reagents should we select? What steps will lead us from point A to point B? Right, so we're going to we've already started looking at these in each of these chapters, and we've even tried to tie it together a little bit here and there. But here we're going to try and really go into more detail in that and try and expand it into multiple step syntheses. So you've probably already heard me use the term synthetic toolkit before, or synthetic arsenal. Each of these chapters where we've learned types of reactions, we've been adding tools to our toolkit. We've learned ways that we can go from one functional group to another, to change the carbon skeleton of a molecule and do things like that. That's basically what we're going to use in this chapter as well. We're just going to tackle some bigger projects, essentially. For instance, look at this example here. We are starting off with an alkene. We're trying to get to this product over here that has two bromines on it. So basically, look at what functional groups we have. And ask yourself, well, how's this molecule changing? Where are the parts from this original reactant that we can still see in our product, and what's different? All right, so for example, you'll notice that we're starting off with an alkene. All right, the carbon skeleton's still there. We still have these four carbons connected here, 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 and here. All right, so this methyl group here is the same as this one up here. This one down here is the same as this one here. And this carbon over here is this carbon here. All we've done is we've added two bromines across that double bond. And so now that you recognize that, you just have to think, well, what reagents do I need to add two bromines across a double bond? Well, you see that starting from your double bond, we need to go back to that chapter on addition reactions and look at how we do a bromine addition. All right, so for example, you would react your alkene with bromine in carbon tetrachloride, and you would do this in the dark. So you use carbon tetrachloride, of course, to make sure it's only bromine reacting, so you avoid a hydrohalin reaction, and you do this in the dark to avoid any radical byproducts forming. So again, my point here is that this was just a one-step synthesis, but we've already seen how to do one-step syntheses. All right, so I don't know if you guys have noticed, but at the end of each of these chapters, I've been putting together these reaction wheels that summarize all of the different reactions that we covered in that chapter. So starting with, going back to substitution reactions, addition reactions, and our elimination reactions, all of those should have reaction wheels at the end of your textbook chapter, and I believe in most of those lecture videos you should hopefully see that at the end of the PowerPoint. But each of those steps is a one-step synthesis. All right, so we're going to again practice that, but then also see how we can build up to multi-steps, just combining each different pieces to make the whole. All right, so if you're not immediately good at this, don't panic. That's normal. This takes a little bit of practice, and so I'm going to show you again some tools to help practice this and get better at it as well. Okay, now we those reaction wheels, and oftentimes when you make flashcards and things, you're kind of memorizing reactants, products, and reagents. It's helpful to also know the mechanism. That might save you with some brain space in terms of understanding sort of the nuts and bolts of how things work. Instead of having to memorize every situation, if you find yourself in a weird situation and with an unusual reactant that you haven't seen before, understanding how the mechanism works will usually get you through those situations. It'll help you reason through what's going on. Okay, so while memorizing these reaction wheels and memorizing every possible scenario is great, it'll probably help you get through problems faster. I do recommend understanding the underlying mechanisms as well. All right, so let's focus on these one-step syntheses that we've already seen. Okay, let's focus on how do we analyze a problem, how do we set up the problem to select the tools that we need to solve the problem. Okay, so first of all, look at your reactant and product. Okay, you want to look at the similarities and differences between the two. Okay, the main two things you're going to look at are functional groups, see how those are different, okay, how they've changed from going from your reactant to product. You typically could, at this point, start to get a feel for what you're trying to do. Okay, we'll talk about carbon skeleton changes in a little bit, but that's the other thing you typically look at when you're analyzing a problem. Okay, those are the two things that you could potentially change through a synthesis. All right. So that being said, you want to pay attention not just to functional groups, but you want to pay attention to in your product, are there any regiochemistry or stereochemistry implications that you've got to consider? Okay, so keep that in mind because that might determine which reagents you have to select. Because certain reagents might do a type of reaction, but they'd give you, let's say, a syn product instead of an anti-product, or a cis product instead of a trans product, and things like that, or a Markovnikov instead of an anti-Markovnikov, if you want to look at regiochemistry. So my point here is that you want to pay attention to that stuff and then use that to help guide you through the problem. So look at this problem over here. We have a cyclohexene or a 1-methyl cyclohexene here, and our product here is 1-bromo-2-methyl cyclohexane rather. So how are these two molecules different and how are they similar? Okay, see if you can identify where that carbon skeleton is kind of overlapping. Hopefully you can kind of notice that that methyl group is a good reference point, right? It's the same methyl group over here, and as is the cyclohexane sort of skeleton over here. So notice that we have this alkene over here, this double bond, and that's missing over here. And instead, we've got a bromine, all right? So ask yourself, what have we changed? Well, obviously we've gotten rid of that double bond and we've added a bromine. What you might not have noticed is that you probably have to add a hydrogen here as well, right? This carbon has, 3 atoms connected to it. Here it has to have 4 bonds, so that what's not shown is that hydrogen is added here. Okay, so as soon as you realize that, then you should be able to figure out, well, we've added a hydrogen and a bromine. So we've essentially done an HBr addition across that double bond. Okay, so now you should be starting to figure out what reagents you need. Okay, so HBr is one, probably a good candidate there. But don't forget to take into account those regiochemistry considerations. Was this a Markovnikov or an anti-Markovnikov addition of bromine? Well, notice that the bromine is on the less substituted of those 2 carbons. So that's an anti-Markovnikov addition. So ask yourself, what else do we need in our reagents to get this reaction to happen this way? If I added HBr just by itself, the bromine would have added to this carbon up here. So hopefully you should have remembered that in order to do this anti-Markovnikov addition, we have to have a peroxide in there of some sort. Okay, and that will encourage the radical mechanism to take over and make this anti-Markovnikov product. Okay, so now let's look at a few multi-step problems. We've actually already seen this back in chapter 9. We looked at a couple of 2-step reactions that would help us move a functional group. For example, we could move a halogen or we could move a double bond, but we've seen some examples of this already by coupling together elimination and addition reactions. So if you start off with an alkyl halide, right, that halogen's a great leaving group. So you can do an elimination reaction to make an alkene, and then do an addition reaction. And by controlling the regiochemistry of those steps, you can get, for example, a Zaitsev versus a Hofmann product, or you could get a Markovnikov versus anti-Markovnikov product, and that controls where that functional group shows up. So here's the different ways we could go through this problem, starting off with this alkyl halide. Okay, we could use a small base like sodium methoxide to make the Zaitsev product, and then we could add, just do a regular Markovnikov addition with HBr, and we would move the bromine to this carbon over here. Alternatively, if we had done the anti-Markovnikov addition, we would have just gone back to our original reactant. Now, with this reactant, we could take a bulky base like potassium terbutoxide here, and instead we get the Hofmann elimination product. Okay. Now, if we use an anti-Markovnikov addition of HBr, we get the bromine over here on this carbon. All right. Now, if we did the regular Markovnikov addition, it's not, we could technically, I guess, well, you're going to get a mixture of products. You could try to go back to bromine over here, but you might get a rearrangement product that would yield this product over here. Okay, so maybe that synthetically that's not the best way to go back. But theoretically, you would get a mixture of these two products. All right, but my point here is that just by changing our reagents slightly, we can get wildly different products, right? And there are different pathways to get to those products. And those are things we can use to our advantage. All right. Now, bromine, of course, is a great leaving group, so that was pretty straightforward. All right. It's also relatively easy to add a bromine across a double bond using or adding a bromine to a molecule by doing an HBr addition across your double bond. In this example, we have an alcohol functional group, and this gets slightly trickier because that OH leaving group isn't a great leaving group. We've got to look at some techniques to make it a better leaving group, and that is typically to tosylate it. We swap out that hydrogen for a tosyl chloride. Okay, so basically, just to jog your memories, here instead of having that OH be the leaving group, the oxygen's a nucleophile that kicks off the chlorine on a tosyl chloride, and it makes an OTS leaving group, which is a great leaving group. Okay, the byproduct, by the way, is pyridinium chloride. So the pyridine, the hydrogen over here, and the chloride both they all crash out of solution as a salt. All right. Anyway, my point is that when you do that, you've got a great leaving group, and then using your base, you can do an elimination reaction accordingly. Okay, though whether you use a small base gives you the Zaitsev product, or using a bulky base, you get the Hofmann product. Okay, so again, the same regiochemistry considerations come into play. You also have to consider then for doing your addition reaction across that double bond, you have different reagents to help you do that, and also help control whether you get the the Markovnikov or anti-Markovnikov addition. Okay, so for example, you can see here that using a borane, you can get the corresponding anti-Markovnikov addition, whereas using mercury acetate or even sulfuric acid, depending on the situation, will give you the Markovnikov addition. Okay, though of course the difference between these two depends on the substrate you're dealing with. In this case, we can just use the sulfuric acid because we're adding our OH group to that very substituted carbon over there. So we don't have to really worry about carbocation rearrangements. So we can go through this carbocation intermediate with this mechanism. See, again, this is where knowing the mechanisms is kind of important. It helps you catch these kinds of pitfalls. Because you might be tempted to take this reactant, and if you wanted to make this product, you might say, oh, I would just do a Markovnikov addition. I'll just use sulfuric acid. But what you might not realize then, by not paying attention to the mechanism, is that that goes through a carbocation intermediate, and the secondary carbocation that you have here would do a hydride shift and become a tertiary tertiary carbocation, which would then give you this product over here. Okay, and that would not go to this product. So instead, a better way would be to do a mercuration-demercuration. Okay, that kind of guarantees the Markovnikov product without any rearrangements. Okay. Likewise, I think we saw back in chapter 9 that in addition to moving a halogen or alcohol functional group, we could also shift a double bond just by changing the order of operations here. We could do an addition reaction first using HBr, or doing it in an anti-Markovnikov fashion using peroxides, and then do our eliminations. Whether we get the Hoffman or Zaitsev product determines which product we get accordingly. We also saw in chapter 11 that we could, basically, if you start off with an alkane, which is a really lousy chemical to be, to be dealt with when starting off a synthesis, the best way to get started there is to introduce a halogen. Okay, as soon as you've got a halogen, now you've got a great leaving group, and there's a whole host of reactions you can do. So it's something to keep in mind. Other things to consider, back in the chapter on alkynes, we saw that there are different ways to cycle between alkynes, alkenes, and alkanes. Okay, we can reduce those down accordingly using hydrogen and a metal catalyst like platinum or palladium. Though that would take your alkyne all the way to an alkane. So if you want to stop at an alkene, you would have to use a poisoned catalyst like Lindlar's catalyst, or use the dissolved metal reaction. And again, there are stereochemistry considerations to consider here as well. This would give you the cis addition, the syn addition. This would give you the anti addition. So something to keep in mind. Okay. Likewise, to go backwards, you'd have to do them in multiple steps, but the idea typically is to take your alkane or alkene, add halogens to it, either through a radical reaction or through an addition, and then you can use a base of some sort to eliminate your way to what you want. So in the case of your halogenated alkane, you can just use any base like sodium methoxide, and that will do your elimination reaction and give you your alkene. Right? But in the case of trying to get to an alkyne, you want to use a really strong base like sodium amide. Okay. Of course, that would give you the alkanide ion, and so you'd want to quench that with water. So that water step is kind of important. Okay. It's also very important that you don't put those two in the same step, because this being a really strong base would readily deprotonate water, and you'd waste your base. So something to keep in mind. Again, this is why knowing the mechanism is kind of helpful. It helps you think about these things. All right, let's try a practice problem here. So look at your starting molecule here. Okay, see if you can identify the parts of that carbon skeleton that show up in your product. And then ask yourself, how is this similar and how is this different? Okay, and then ask yourself how you'd get from from your reactant to your product. Okay, now you're not going to be able to do this in one step. Okay, there's no way to take an alkane like this and add two alcohol groups to it. Okay, but I would suggest maybe gradually working your way from one end to the other. Sometimes if you get stuck, it's sometimes easier to work backwards a little bit. Look at this product and ask yourself, what reactant could have made this? So what intermediate, really, since it's a multi-step synthesis, what intermediate could have led to this particular product? Okay, how do we add two OH groups? Okay, do we have to do them in separate steps, or is there a way to do this in one step? Okay, so for example, maybe you want to consider that there's a dihydroxylation being done here, and there used to be a double bond over here. Okay, and then of course that gets you working backwards. So how do I add that double bond over there? Okay, how do I get to something that can add double bonds from an alkane? Okay, so just pause this video, see if you can think through this, and then I'll walk through it with you. Okay, so if you're back now, you probably hopefully have realized that, well, we're starting with an alkane, so we definitely have to do a radical reaction in the beginning, get some halogens on that just so we can do some eliminations, and get to the alkene that will allow us to do this dihydroxylation. And that's basically what happens, right? We start off with bromine that will add on bromine to this tertiary carbon, either this one or this one, and then using a base, we can make the resulting alkene. We'd have a double bond between these two carbons. Well, then using your MCPBA, you could do an anti-dihydroxylation. Okay, if you want to see the mechanism for this or look at this in more detail, go back to chapter 9. Okay, and so that you then quench that reaction with some acid, but that makes this final product, and that's what you want. So far we've been looking mostly at functional group transformations. How do we move functional groups? How do we change functional groups? The other thing I told you need to pay attention to are carbon skeleton transformations. And we've already seen some reactions that do carbon skeleton transformations, so we'll talk about that in a second. Okay, we're also going to see some new ways to carry out some of the reactions that we'd like to do. Okay, so now what do I mean by a carbon skeleton transformation? The carbon skeleton is the carbon-based backbone of your molecule. It's the part that all your functional groups are attached to. You could consider your parent chain, for example, in any organic compound. You could consider that to be your carbon skeleton. And when you're looking at your reactant and product, typically, in the case of just functional group changes, your carbon skeleton doesn't change. And it's a great reference point for seeing where everything is. How have the positions of things changed? Because again, that gets you thinking about regiochemistry and stereochemistry. All right, but in some cases, that carbon skeleton is going to change. So it makes sense that you want to count your number of carbons. Sometimes numbering them helps. Especially for seeing where things are, where are you adding or losing carbons. All right, that's something to keep in mind. So, as I mentioned, we've already seen some carbon skeleton transformations already. In this example here, we've seen how to add an alkyl group to an alkyne, and in doing so, you extend the carbon skeleton. All right, you're combining the carbons from your alkyl group from your alkyl halide, and you're adding the carbons from your alkyne. Okay. Now we've also seen ways to cleave a molecule and therefore shorten the carbon skeleton. So depending on if you have an alkene or an alkyne, you could do an ozone cleavage, and that will give you the corresponding aldehyde, or either, like in this case we've got aldehydes, but you might have a corresponding ketone, right? It just happens that we have aldehydes here because there are hydrogens attached to these carbons. Of course, in the case of an alkyne instead of an alkene, we would get the corresponding carboxylic acid products, okay, or carbon dioxide in the case of a terminal alkyne. Okay. So with that in mind, let's see if we can apply that. So here we have an alkyne of one sort, okay, and now we've got two aldehydes that we've made, okay. So see if you can connect these two, but note that this entire synthesis is going to take more than one step, okay. So you can kind of tell that, because if you think of this backwards, we've got two aldehydes here. We just talked about how we could do the ozone cleavage of an alkene to get these two aldehydes, which means that this carbon and this carbon were once connected to each other through a double bond. Okay, so that would be the intermediate that you would have just before we get to these two products. Okay, so see if you can draw that and go from there. So it might sometimes help to label your carbons to try and see where they all fit together going from your reactants to products. So if I'm trying to draw out my intermediate, I could basically start off by starting off with those familiar functional groups. So I've got this tert-butyl group over here, so let's draw that out first. Okay, and then I've got that carbon coming off of it, another carbon coming there. Now remember, this carbon, which is this carbon here, is connected to this carbon. So we have a double bond here, right? These were probably connected by an alkene, not an alkyne. If it were an alkyne, this would be a carboxylic acid and not an aldehyde or ketone. So anyway, so this carbon was this carbon here. This carbon is this carbon over here. And so we're going to continue on from there. So we've got an ethyl group coming off of that. Okay, and so that's kind of our carbon backbone that led to these two products. Okay, so you now have to ask yourself, well, how did we get from here to here? If you count the number of carbons, if we label this, you'll notice that this is not the same number of carbons, right? Here we have, going from our tert-butyl group, we have 1, 2, 3 carbons coming off of that, and that's the end of our alkyne. Whereas here we've got 1, 2, 3, and we've got to add on that ethyl group. So, think back to that chapter on alkynes and ask yourself, how could you extend the carbon skeleton with that? So, for example, if you take this alkyne functional group and you want to extend that carbon skeleton by 2 carbons, we essentially want to have an intermediate that looks like this. So here's our alkyne, and there's an ethyl group coming off of that. Okay, so that tells us that we probably have an intermediate that looks like this. Okay, going from here to here should be pretty straightforward. Notice that we have a trans alkene. All right. We could have done this also with a cis alkene. So I've drawn a trans alkene here, but I could have used a cis alkene as well to go to these products. So there's actually more than one way to get the right answer here. Okay. All right. So feel free to pause this video if you want to think some more about it. But on the next slide, here's the answer. So that first step, these first 2 steps will convert your alkyne and add that ethyl group. So basically, your sodium amide will turn this into an alkanide ion, which then does an SN2 substitution with your ethyl, let's say ethyl chloride or ethyl bromide, whatever halide you're using. And it adds on that ethyl group, so you get that internal alkyne. So using hydrogen and either a poison catalyst like Lindlar's or using sodium, dissolved sodium in ammonia, you will make a corresponding alkene. It actually doesn't matter which alkene you use. You could get the cis alkene using your Lindlar's catalyst, or you could get the trans alkene using the dissolved metal reaction. But the bottom line is your alkene can then undergo ozonolysis using ozone and dimethyl sulfide, and that'll give you that final product you see here. Okay, so you can see that this took multiple steps, but breaking this down to chunks makes this a lot easier, and sometimes working backwards also makes this a little bit easier. Now, don't panic. This is an acquired skill. It takes a little while to get the hang of this. That's why we're practicing this stuff. All right, so don't panic if you're not immediately great at this stuff. Okay, it takes a little while to get the hang of it. So, how do we approach these types of problems? As I pointed out, the 2 key things you want to look for are how has the carbon skeleton changed and how have the functional groups changed. So look at your reactant, look at your product, ask yourself how are these 2 things similar, how are they different? Okay, and specifically look at your carbon skeleton and your functional group. Okay, and basically then just see if you can kind of work your way from one end to the other. Ask yourself, what do those intermediates look like? And then ask yourself, what steps do I need to take to make those intermediates? What reagents do I need to use? All right. Pay special attention in those intermediates to regioselectivity and stereoselectivity. All right. Just ask yourself, where does my functional group need to be? Where does this reaction take place on this molecule to give me the product that I want? So let's try another problem out. Okay, so have a look at this reactant in this product. As I pointed out, see how they're similar, see how they're different, and ask yourself, how is the carbon skeleton changed, and then how are the functional groups changed? Okay, so if you've paused this video, you've come back now. probably hopefully have noticed that the carbon skeleton is a little different. And again, if you're having trouble seeing it, I recommend labeling your carbons. So, if you start numbering carbons from your tert butyl group here, you've got 1, 2, 3 carbons to get your alkyne. And if we follow that here, we've got 1, 2, 3. So our alkyne used to be between these two carbons, but you can see that the carbon skeleton has extended with this methyl group here. Okay, so that might be an interesting first step. We might want to take this alkyne and using that reaction that we know that extends that carbon skeleton, add a methyl group to the end over here. Okay, and so you know how to do that. We saw that in the last example. Okay, then at that point, you can kind of work backwards on this, but you can ask yourself, is there a way to add 2 bromines to this? Okay, and what would you do there? Would that work with an alkyne, or do we have to use an alkene? Those are considerations you want to take into account. Also, notice that the 2 bromines here are cis to each other. Is that how bromines add? Okay, so you want to say that you want to pay attention to the stereochemistry here, because they've taken the time to show you that stereochemistry. So that could hint that that might be something you need to pay attention to. All right, what reagents do you need? What starting material? What's the previous intermediate that would give you this specific product as opposed to an enantiomer or diastereomer off it? Okay, so again, pause this video, think a little bit more about this, but we can go from there. All right, so if you're having trouble seeing those intermediates, I will point out, of course, that one of the intermediates we wanted to make was, like I said, to extend this carbon skeleton by 1 carbon. So ask yourself, all right, what steps do I need to get from here to here? Okay, and in fact, it's 2 steps, right? You want to use sodium amide, and then you want to use some methyl halide, let's say like methyl iodide or something. Okay, and that will get you to that product. All right. Now, as I mentioned earlier, you want an alkene. Okay, you have to think, do I need an alkene or an alkyne? The answer is an alkene, right? You can do a bromine addition across your alkene to get this product. The thing to watch out for, though, is to remember that bromine addition across an alkene is an anti-addition, right? We've done a lab on this. So these bromines are shown cis to each other. But remember, when they add across that double bond, they're actually trans to each other. So you might want to rotate around this carbon-carbon bond here and get these 2 bromines trans to each other to give you an idea of what the original alkene looked like. Okay, and so, spoiler alert there, it's going to be a trans alkene, right? If I move this bromine to this side and that methyl group over here, that methyl group is trans to the rest of this molecule. Okay, so in other words, my intermediate here look like that. Okay, so ask yourself, what reagents would I have used to get from here to here, and what reagents from here to here? Okay, I think this one hopefully should be pretty straightforward. You're just doing a bromine addition, and you want to do this in carbon tetrachloride in the dark, right? You don't want any halohadron byproducts, and you don't want any radical byproducts. Okay. For this one, ask yourself, how do I go from an alkyne to the trans alkene? Okay, you can't use a poisoned catalyst like Lindlar's here, because that would give you the cis alkene, right? You have to use your dissolved metal reaction. So there we go. So here are those steps, right? So you first, those first 2 steps will get you add on that methyl group. That 3rd step will give you the trans alkene, or I guess they call it the E-alkene, but I guess technically it's trans because there's 2 hydrogens on there. And then, of course, that last step will get you those 2 bromines. Okay, so you've probably noticed in the last couple of problems, it's been helpful to work backwards in some steps. This is known as a retrosynthetic analysis, when we kind of go backwards from our product and work our way back to the reactant. Okay, because sometimes when you're just trying to work forwards, it's kind of hard to figure out what you're doing because there's so many possibilities. But oftentimes when it comes to making a product, there's usually only one or two viable options to make that product you want. So sometimes that retrosynthetic analysis is a better approach for doing these problems. And again, you don't have to be limited that way. I think sometimes problems are easier to solve if you work both angles. You ask yourself, how do I, what intermediate makes this product, but then also, what intermediates can I make from this reactant, and you just try and meet in the middle. There's multiple approaches here is what I'm getting at. All right, so let's basically try this out again. So here we have this alcohol, and we want to wind up with this alkyne. Okay, so basically you can kind of, first of all, look at your carbon skeleton, right? See how if you've got the same number of carbons, is it different or not? Right now it looks like coming off our terpyl group, we've got 2 carbons over here, and that's the same case here. So our carbon skeleton's not different. I guess the key thing to notice is that we've got an alcohol group here, and instead here we've got an alkyne. Okay, so that's the key functional group changing that we've got. Okay, so I guess we've already answered that question. Okay, so we could look at, start off with our alcohol and ask ourselves, okay, what can we do with this alcohol? What can we make? And then from one of those products, what can we make from that? And so on until we get our alkyne. But that might be tough to do. There's lots of reactions you can do with an alcohol, right? So it might be better, since there's only so many reactions that can make an alkyne, to work backwards here. What can we make an alkyne from? Right? Typically, we do some sort of elimination reaction with a dihalide, right? So this is the only way we know how to make an alkyne. So this was probably one of those intermediates. Okay. So so basically, what probably happened here was we probably had a vicinal dihalide, right? It makes a little bit more sense in that it's relatively easy to make a vicinal dihalide, vicinal, I don't know, I might be mispronouncing that, a vicinal dihalide, because you could easily add these 2 bromines across a double bond that was over here. Okay, so that's something to keep in mind. And again, if you're working retrosynthetically, that might be the previous step. Okay, what does that alkene look like? All right, and then you can keep on working backwards. How could we make that alkene from this alcohol? And that's basically what we're doing. So now when you're doing a retrosynthetic analysis, it sometimes is a little bit difficult to keep on writing backwards, because you don't know necessarily how many steps you're dealing with, right? So in this case, we will sometimes see this type of arrow. This wide-bodied arrow is distinct from your regular reaction arrow in that it means the opposite. A regular reaction arrow has a reactant on the left and you have the product on the right, and it just means this reactant produces this product. When you see this kind of arrow, you basically have your reactant and products flipped. Okay, so what it's saying is that this product can be made from this reactant. Okay, so be wary of the type of arrow you see when a retrosynthetic analysis is in front of you. Okay, or when you're doing one, feel free to use this type of arrow to show that you're working through this problem backwards. Okay, again, it just sometimes makes things easier to write out if you're kind of working backwards like that. Okay, so let's continue on. So our alkyne can be made from this vicinal dibromide, and this dibromide, of course, can be then made from an alkene, right? We can easily just add bromine across your alkene to make this dibromide. All right. So then ask yourself, can I make this alkene from my original starting material? Probably not directly. Alcohols are pretty lousy leaving groups, but we already know a way to turn an alcohol into a better leaving group. And once we do that, can we do an elimination reaction to make this alkene? Well, yes, we can. All right, so So far, we started off, we had that alkyne, which comes from our dibromide, which comes from an alkene, which, if we're working fours from our alcohol, we can make that a better leaving group by tosylating it, when we know how to do that using tosyl chloride and pyridine. And of course, as I mentioned, you can just do an elimination reaction to produce that alkene. Okay, and then of course follow the respective steps to go on to your final product. Okay, so basically, if you were to take that and write that out, instead of drawing all the intermediates, you could just summarize it in these steps here. So we convert our alcohol into a tosylate by using tosyl chloride and pyridine. We use a base of some sort to form the corresponding alkene. Okay, here we've used a bulky base, but to be honest with you, it doesn't doesn't really matter which one we use. In the previous step, we used I think sodium methoxide. Actually, if I go back a slide, you can see that. So it doesn't actually really matter. Since you're leaving groups on that terminal carbon, you don't really have to worry too much about regiochemistry here. Okay, and then of course with the resulting alkene that you get after that step, we'll add bromine across that to make the corresponding dibromide, and then using excess sodium amide, we would get the terminal alkanide ion, which we can quench with water to make the resulting product. Okay, let's try another one out. Here's a similarly done reaction. We're adding dibromides here. Actually, this is very similar to a reaction you've already seen. So yeah, go ahead and try this one out. And please pay attention to the stereochemistry here. Okay, so actually this is going to be very similar to a problem we've already gone through, but there's only one slight difference here. Okay, so feel free to pause this video and try this out yourself. All right, and if you're back, you probably noticed that this is very similar to that problem earlier where we had the cis dibromide. And if you recall, for that to work, we had to have the trans alkene in the previous step, right? But here, these two bromines are trans to each other, which makes sense when you do an anti-addition, which means the original alkene had to be cis. It had to be in this sort of orientation here. So keep that in mind, right? Basically, if we're going backwards, we're doing a retrosynthetic analysis, this was our dihalide. Here's the alkene, that cis alkene that makes it. Okay, and of course this must have come from this corresponding alkyne, which you can basically you can add that on from your original reactant. Okay, so they redrew this molecule here, I think just to make it a little bit easier to see that step. This is the same thing as this molecule here. Okay, so for each of these steps, of course, you can then think about what reagents do I need? What reagents do I need to take this alkyne and make to extend the carbon skeleton by this methyl group, right? You just use sodium amide and a methyl halide of some sort, like methyl iodide or methyl bromide or whatever. Okay, then ask yourself, from that product, how can I make this cis alkene? Well, we know that we can do that with a poisoned catalyst, like Lindlar's catalyst. Okay, because that would add the hydrogens on the same side. It'll be a syn addition of hydrogen. Okay, and then of course we just do a bromine addition. We're just adding bromine in the dark, in a solvent of carbon tetrachloride, and that's that. Okay, so that being said, by now hopefully you've started to build up that synthetic toolkit I've mentioned, and if you want to, it might be good to compartmentalize it into sections, and we've kind of already started doing that just by looking at types of reactions. We've kind of classified substitution reactions versus elimination reactions versus addition reactions, and I think doing that compartmentalization helps a lot in terms of trying to make this easier to memorize. But I would also try and compartmentalize it into reactions that affect the carbon skeleton versus reactions that affect functional groups, since those are the two key categories that we use to analyze our reactants and products. Okay. Okay. Now that being said, how do you get better at this? As I mentioned, this is an acquired skill, and to be honest with you, really the only way to get good at this is to just keep on practicing it. So, as I said, you don't panic if you're not immediately great at this stuff, but you will get better as you practice it. And so I recommend just practicing it more and more, and you'll get better and better. Okay. So if you want to do this on your own, or if you're working in a study group, you can essentially make your own problems. Start off with a relatively simple compound, and make a few just try to change a functional group at a time, or extend the carbon skeleton. Just do like simple steps. If you're working with a classmate in a study group, just exchange problems with each other. Just give your classmate the original reactant you started with and that final product you wound up with. And again, it doesn't have to be too complicated. You could do this in just just say 2 or 3 steps. And then have them work out, how did you get from A to B? How did you make that final product? Okay, and then of course, do the same with them. Have them give you a problem like that. And that's a great way to practice. Okay. I mean, you could also kind of do this yourself, though. I guess you kind of know the answer when you do it yourself. So I guess one thing to do is perhaps make a few problems and then set them aside for a while so you kind of forget about them, and then look at them again. So I think this is probably a little bit easier to do with a study group rather than on your own. Okay, so feel free to talk to your classmates and just send each other problems every now and then. Okay, so here's an example, right? So let's say we start off with acetylene, right? Just think of a few simple reactions you could do to acetylene. So for example, we can extend the carbon skeleton, to make it, add on this methyl group, right, to make it propyne. Okay, and then from that we could use Lindlar's catalyst and hydrogen to make the cis-alkene. Okay, and that's 2 steps, right? Oh, sorry. I guess it looks like I skipped a step there. It looks like that we did a second equivalent of sodium amide and methyl iodide to add on another methyl group. So actually, we have 2-butyne as our alkyne here. Okay, but then we take that, we react it with Lindlar's catalyst, and we make cis-2-butene. So what you would give your classmate then is you would say, all right, I started off with ethyne, and I wound up with cis-2-butene. How did I get from here to here? Okay, and that's basically this gives your classmate a chance to work out how to get from here to here. Right? They'd analyze it, saying all right, well, we've changed the carbon skeleton. How can we extend the carbon skeletons with the starting alkyne? How could we add these 2 methyl groups? And then how do we go from that alkyne functional group to an alkene functional group with this specific stereochemistry? Okay, that's how someone who hasn't seen this problem yet would analyze it, and that gives your classmate an opportunity to just have an extra practice problem. I mean, of course, there are practice problems you can use in your textbook, and I definitely recommend trying those out, especially with the solutions guide to check your work. But if you run out of problems, this is a great way to get extra practice. Okay, now one thing to watch out for is that there oftentimes is more than one way to get the right answer. Okay, sometimes you can see here we've got 2 possible pathways to take that reactant on the left and make the product on the right. Okay, so typically, if you had this problem in real life and you weren't sure which to do, my advice to you is to pick the one that has the fewest number of steps. All right. Remember, every time you're making something synthetically, you're going to get a few byproducts in there, right? And you want to clean up that intermediate to avoid those byproducts giving you, even more byproducts, right? So the problem with that is that you decrease your yield, right? Every time you clean up your intermediates, you're getting rid of those byproducts. You might lose some of your actual product in the process. And my point is that the more steps you have, the lower your overall yield because you keep on losing material as you go through. Okay, so when in doubt, pick the solution that has the fewest number of steps. But that being said, just be ready to recognize more than one answer. Since your quizzes and exams are all multiple choice, you have to realize that sometimes the immediate answer that you come up with might not be the one that's listed in the multiple choice. Okay, so you have to be ready to recognize more than one answer. Okay, and that's it for this chapter. So let's go through these additional practice problems. But yeah, like I said, it's pretty much just practicing this stuff. Just get comfortable with looking at a reactant and a product and figuring out how did we get here? What reagents do we need? What intermediates do we make? Or alternatively, if you're given a reactant and the reagents, ask yourself, okay, what will this make? Okay. All right, so let's try this out. So here we have a reactant on the left, we have a product on the right. Go ahead and analyze this in terms of its carbon skeleton. All right, so if you count carbons here, here's our tert-butyl group we can use as a reference point. Okay, and so we've got 2 carbons going there with a methyl group coming off that first carbon. Here are those 2 carbons that we had, and here's that methyl group that we saw earlier. So the carbon skeleton isn't changing. So what is changing? Well, we've got a bromine here and an alcohol group adjacent to it, right? So that's essentially what we've got to add on to our molecule, though obviously that's not going to be easy to do with an alkane. So you might want to approach this retrosynthetically, okay? Now, at first glance, this might seem relatively straightforward. You'd say, okay, I've got a bromine and an alcohol group. I can add that through a halohydrogen reaction, right? So if I have an alkene with the double bond over these 2 carbons, I just add on my bromine and alcohol group, no problem, right? I just use bromine in a solution of water. The problem with that is when you start paying attention to your regiochemistry, notice that your bromine is on your more substituted carbon and your alcohol group's on your less substituted carbon. Okay, so this is a little tricky because you have to remember with your halohydrogen reaction, it's the other way around. Your water is your nucleophile, and so the alcohol group winds up adding onto your more substituted carbon. Okay, so if you want to get this product, you may want to look for an alternative pathway. So this problem is a little trickier than it looks at first. Okay, so what I recommend is using MCPBA to make an epoxide and then have bromide as your nucleophile. So perhaps using hydrobromic acid. Okay, so here are all the steps. Basically, you start off, your alkane is not going to be reacted at all. So your first step is to get a halogen on there through some radical reaction. You could use bromine. The problem with the bromine is that it will probably do a poly substitution. You'll get, you want a bromine at that tertiary site. That's a great place for it. But you might get more than one bromine. So they've used NBS in the presence of light, so that's probably a safe option. You can then do an elimination reaction to get the corresponding alkene over here. All right. They use a bulky base as opposed to, let's say, sodium methoxide or something like that. I think that's to avoid any rearrangements. You want to ensure that you're getting that Hoffman product. Okay, it is possible to get a Zaitsev product where your carbocation rearranges and you wind up with a tertiary carbocation over here. So that's why they've used a bulky base. Okay, so if you used sodium methoxide, that's why you shouldn't use it. Okay, and then like I said, you can take that alkene, convert it into an epoxide, and then add HBr to that, and the bromide from your HBr will be your nucleophile, and that's why it adds to the more substituted carbon there. Okay, so like I said, that one was a little bit trickier, but this is a good example of why you want to pay attention to regiochemistry. Now, the next couple of problems we're going to see have suggested answers that involve topics you're going to learn in the next couple of chapters. Okay, so don't panic if you start seeing, if you flip to the answer side and you're like, wait a minute, why are they, what is this thing that they're using? We haven't learned about Grignard reagents yet. That's in the next chapter. So don't panic, all right? All right, so and again, there's oftentimes more than one right answer here. So I would say try and do this using the tools that you know for now. Okay, so notice that we have an epoxide here. So again, you could probably make that using MCPBA and work backwards from there. So there was probably an alkene over here, right? Notice the carbon skeleton is also extended. So ask yourself, how could you have extended that carbon skeleton? All right. So if you want to do this, it looks like both options involve using a Grignard reagent. So I guess this is one of those problems where you probably wouldn't have been able to solve using your tools from this chapter or from previous chapters. So if you didn't get this one, again, don't panic. I would say come back to this problem after you've looked at chapter 13. Okay. Likewise here, this one also is going to use phosphorus tribromide. That's again another reaction involving alcohols. So you can use that information I've listed here to help you out. But again, if you can't solve this problem, don't panic. This will make a lot more sense after we do the next chapter. And so that's essentially what they've done here. They've taken, they've converted this alcohol group into a better leaving group here. They've basically, used a bromide. You could have also done this with, by converting that into a toslate group. So if you did that using the method that you know of, that's fine too. All right. It looks like then they use a base to eliminate that. You basically form your alkene over here. They've used just a regular base instead of something bulkier. Again, I think in terms of rearrangements, I don't think you have to worry too much about it rearranging too far. Either way, you're going to form your double bond over here since your leaving group is on that terminal carbon. The next thing they do with that alkene, of course, is it looks like they want to encourage the Zaitsev product using a mercuration demercuration, but instead of using water, they use ethanol, and that's how they add on an ethoxy group instead of an alcohol group here. Okay, so they've done that. And that's basically it. Again, there's more than one right answer here. This is just one possible way to do this. All right. Well, that's it for this chapter. I recommend, since we have an exam coming up, definitely go through your old quizzes. Definitely try the Chapter 12 practice quiz that I've put up, and especially, make sure you're practicing some of these synthetic problems. And don't panic about some of these additional practice problems since they were a little bit beyond the scope of this chapter. I'll limit the questions on your exam to the synthetic method seen before. All right. Well, as always, if you have any questions, let me know, and good luck.